Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about object tracking and we will continue this discussion today. In the last lecture, we discussed about Kalman filtering, where Kalman filters, they are a kind of a special case of a recursive Bayesian trackers. So that we discussed, and we see that essentially in the Kalman filter, what we consider that there are models for object motion. So we call them states. So there are states of the target objects, and the state from one time instance to another time instance, it is changed by some linear equation. So this is the state equation, if I say, for the object to move to a new state. State here means the position, location, velocities, etc. And the other thing is that you are also measuring, you are observing the object and also some projection of its state, if I consider, that is in the image. So if I say that suppose this is your, say, tth frame or kth frame, k minus 1th sequence, and you have an object state or object location, velocity, etc. and you have, say, computed its corresponding motion values, and applying that motion model, you can say that you can predict what could be your state at the kth instant. So this equation provides you that particular relationships. And here, as you see that in the Kalman filtering, we consider it is governed by a linear relationships, functional relationships of the state change, and there are also noise that needs to be considered under the Bayesian framework, and this noise is taken as a Gaussian noise. So it's a normal distributions, and in the multidimensional Gaussian noise for a multidimensional state representation. And then what we do, the other instance, what is considered that at the kth instance, once again this object could be observed, or its, as I mentioned, projection of that state, its location, etc., velocities also. This could be observed or measured here. So that is something, this observation we consider that is, the observation is zk. So this projection is considered from xk. If I multiply with hk, then you get zk, and there would be again some noise associated with it. So this is the model. So what in the Kalman filtering we do that, we know that what is the probability. So this is the update part. What is the probability of xk, or we also we have that model that there could be again some variation in the probability. So this is the xk minus 1, but there could be noise associated with this also estimation. So there is a probability distributions which is the estimation of this, again given the past observation. So given this, all this quantity, then as I said that you predict the things. So this is the prediction part. Prediction means what is the mean and what is the variation, what is the variance of this particular state change, and then when you are observing it, based on that you are updating this prediction. So this is the update part that we have discussed in the last lecture, and there is a Kalman gain which actually updates the predicted one by this factor, by multiplying with the observation and also the measurement, projected measurement of the predicted one. So what is the difference? So if I project the predicted one, then there is a difference. If I multiply with the gain, so that will give me the mean, and similarly this gain is also used for modifying the covariance matrix in this way. So, these computations we discussed in the last lecture. Now, today we will still continue this discussion on Kalman filtering, and we will look at a different interpretation of this point. So, in this perspective of another perspective, we can see that Kalman filtering is a kind of a decision fusion process which handles uncertainties. As let me explain that, as you have seen that there are two kinds of observations, decisions. One is due to prediction, you have a position, and again due to measurement also you have another kind of, from the measurement also you can try to make some kind of decision. So, how to fuse both of them so that gives you the ultimate update operations using the Kalman gain. So, we will see that this kind of modeling of handling uncertainties, that could be well explained also using this framework. So, what we consider here, let us consider there are multiple pairwise uncorrelated noisy measurements or estimates. Now, which means that now you have basically the measurements and estimates, they are uncorrelated. So, estimates are those things. So, let us a linear combination of estimates minimizing its variance, that would be considered under the Gaussian probability density function. That is the case for Kalman filtering, and handling prior in tracking is special case. So, it gives you the prior distributions of the position, and then you are observing that where you are there. So, two different observations. One is prediction of states of motion from previous frame, like this. xk1 is given fxk minus from the k minus 1 at the instant. So, this is one kind of prediction, and we are not showing noise for the brevity, and also measurement in the current frame. So, correction through decision fusion, which means that if we consider a measurement, say zk, and from there we may try to estimate xk2. So, this is a relationship, so which may cause this zk. So, this is two relationships, and what we want to do, we want to consider xk as a from these two informations. We want to measure xk from these two informations. Now, what we can see that in this decision fusion process, these are the linear combination of these two, and very intuitively we can say that the higher the variance, the smaller should be this coefficient. So, which means that coefficient should be inversely proportional to variances of estimates. So, every estimate has certain, as I mentioned, there will be a variance. So, that is taken care of, and they determine this, and finally, that is how the update final decision has been taken. So, in one dimension, let me explain this thing. So, suppose you have this set of pairwise uncorrelated random variables. That means you have n such estimates, if I say n such probabilistic estimates, x1 to xn, and they are all uncorrelated, pairwise uncorrelated. So, finally, you want to consider the observation or aggregation of these decisions, or fusing this decision as a linear combination of all these estimates. So, they are estimates of the same entity, and you are taking the linear combination of these estimates. So, sum of ai xi, that is what we are showing. So, y is a random variable and a linear combination of xi's that I have mentioned. Now, if I take the mean and variance of y, so this is related with those set of random variables from which this estimate has been taken as a fusion of those estimates. So, you can see that the mean because of this linear combination would be ai mu y, and similarly sigma square y would be ai square sigma square y, because they are independent. That is what pairwise independent. So if a random variable z is pairwise uncorrelated with this, it is also uncorrelated with y. So this is another thing that also you should theoretically you can show, and that is used here in this case. So the problem here is that what is the optimal linear combination? So what is optimum in the sense that which linear combination will give me the minimum variance of y. So that is what, and those coefficients are called optimal coefficients. So it can be shown that this, as I mentioned, that this coefficients, it's a linear combination, it's a convex combination, and all the, so convex combination means sum of this coefficients should be 1, and all of them are here positive, and here ai is inversely proportional to its variance of that same random variable. So you can see this is a weighted operation, it's a fraction of that. So this is a very simple result, it can be proved easily. So finally your optimal estimate would be this linear combination with this set of coefficients. So I have discussed just in one dimension. In multidimensional space, naturally the computation would be a bit more complex, because the variances, the way the linear combination takes place in multidimensional space, it is not like that. There has to be a quadratic modifications of matrices. So that's what we see, that each covariance matrix is modified by this quadratic term. So the linear combination of mean is very simple with this fusion. So basically it's a matrix operation, which is equivalently showing that kind of linear operations for this decision fusion. So this is the mean of the variable y multidimensional in the multidimension, and this is the covariance. This is how it gets affected. So there once again the same theorem is also true for the multidimensional variable z. It is also pairwise uncorrelated with if it is pairwise uncorrelated with all these variables, then also it is uncorrelated with y. So the problem here is that we have to minimize the mean square error of the variance. So this is the covariance matrix of y. So we want the expectation of this. So to minimize MSE, mean square error, so you take so that it is basically the distance y minus mu y transpose y minus mu y. So you are going to minimize this mean square error. So that is in the multidimensional perspective you are doing. So it's a scalar value, as you can see here. It is not exactly the variance, it is the distance estimate of y. It should be minimized with respect to this, and the solution would be that this is sum of ai equal to 1, and this is a combination. So actually there are all these observations are there, as you can understand. So it is yi, every variable would be yi and mu yi, and you take the respective expectation of that, so average of that. So you can see also that the solution structure is similar. So here again it's a kind of as we say equivalent to convex combination of the one dimensional case, and you can see also that even the covariance inverse of the covariance matrices, they dictate this linear term or for the I should say the matrix, the transformation from X to contributing transformation of the respective random variable to forming. So when we so this is optimal estimate, and for two variables, because as you see that we have two conditions. One is from the motion model, there is a prediction. The other is from the observation, again you have some estimate. So you have these two cases, so prediction x1 with f and prediction of measurement z that we have, and this is a relationship. So finally the correction would be in this form. As you can see that I have taken x2 minus x1, that kind of inversion, but no, you have to estimate it. It may not be invertible operations from the point of view of relationships, but there has to be some means of estimations from this to this, and then it is the correction term or update term that is what used here. This is the Kalman gain, and this is how the Kalman gain is also relooked here under this framework. So the linear combination is rewritten for Kalman gain, that you understand. And you can measure also uncertainty. So this will be the uncertainty, and this uncertainty will be the finally, that is we consider that should be the optimal uncertainty. Now this I have discussed under the concept of Bayesian tracking probabilistic model. But there could be some non-probabilistic approaches. Once again, any non-probabilistic approach has very direct relationship, very I should say close relationship with probabilistic models. We can find it out, but we handle it in a non-probabilistic way. And one of this method is called graph-based method. So what we do in the graph-based method, that see, consider the objects in consecutive frames when it is in motion. Now there are possible positions of the objects in subsequent frames. Because of the measurements, you may consider some of the positions, those are the candidate positions. You do computations and you are searching. So you are while searching, you can consider some of those positions as candidate positions, because there are certain search score what you use during this motion. So here like in the generative model, we have discussed that this correlation coefficient, normalized correlation coefficient could be a score. So if you have say object here in this frame, and this is a target frame object, and in this frame there could be several such objects, and you can consider that what is the score, correlation score between of the same windows, and each one could be candidate with certain score. So what we consider here, that we try to establish the possible connections, but there could be another object which may look like this, and score will be so low that we don't consider this is a candidate one. So we express this relationship in the form of a graph. If they are associated, and since there is a temporal direction, so we form a directed graph, and the weight would be that score. And in this way, we form a directed weighted graph. So in this graph, as just to summarize, that objects in a frame, they form nodes, and between two correlated objects in two different frames, an edge is formed, as I mentioned, and the measure of correlation provides the weight. And temporal direction, as I mentioned, provides the direction of the edge. So the problem here, the computation is that trajectory is the longest path in a graph. That means your evidence gets accumulated. There are several frames, and in each frame you have certain candidates, and for each one there are candidates. So finally it's a chain of I should say edge and nodes that you can form connected one, and it is represented as a graph. So if you had some strong evidence, so what is the longest path between this to this? Sometimes this destination node may not be also explicit. So you may consider on all possible candidates at the last frame, and then for each pair of source to that you can compute the length, and whichever is the longest you consider that gives you the trajectory for this object. So as you can understand, this is a kind of offline computations, or buffered computations when you are trying to get this trajectory. So just to explain it, illustrate it a bit more pictorially. So as I say that suppose this is the source object in frame 1, and these are the candidate objects. So like frame 1 has some kind of kernel correlation with this point 0.5, or with this one is 0.4, and say with this one is 0.6. Similarly, you form all these edges, and each one has a weight. I have not shown them, but there would be some weight W by computing these things. So this will give you, as I mentioned, this kind of directed weighted graph. And these are the possible destination nodes, locations. So you compute the longest path along it. So this is the problem statement once again. Given a source node, longest path of the graph obtained by dynamic programming gives the path of the object. Now this method is explained, or you can read this algorithm with much more details in this particular paper. So it is applied for ball detection in a broadcast video. So as you see that this ball is a very small object, and there could be several candidates what you detect because of several noise, etc. They are all candidates of ball in the next frame. But finally, because of this elimination, because of these accumulations, you are associating, while forming graphs, you are considering each candidate. But after that, when the trajectory is recovered, then actually this ball is, this candidate is selected considering the overall accumulation of your standard, accumulation of your evidence. Now, this method can be also considered for some kind of semi-real-time or real-time applications, where now you do not build up evidences for for so many frames. Rather, you start dynamically accumulating these evidences, and judiciously you go for expanding the nodes by expanding the graph, or judiciously go for a single path tracking. So we call it multipath, single path, multipath tracking. Basically, multipath tracking. So at certain point, these are all single path tracking. If I consider, that means when you have a very strong evidence, you just select that candidate only. That is the point. But whenever there is a confusion, that means there are equally strong evidences. So you choose all the options, and you go on exploring that space till you find that at certain point, the evidence has become again stronger one at certain point. So there you consider, so then you select that one, and then all the paths, so all these things will be discarded. Only the path following this will be taken, and it will be explored further. So this is a kind of online processing or on the fly processing that you can take care. So just to summarize this particular technique, that it's a greedy on the fly approach, and it uses the maximum kernel correlation score to find object location, and if this score is quite strong, then of course you go for single path tracking. So if the Cmax of a block greater than threshold value, you start continue with top key candidates, or if else start continue with the single path tracking. So here actually, if I say that it is basically the other one, so you just switch over this one. So if it is less than threshold, then you go on doing this multipath tracking as it is shown here, and if it if it is greater, then you continue the single path tracking. So that was one kind of approach I discussed, the graphical approach. So next, the approach that I'll be considering, that is discriminative tracker. So in this case, what we consider that we pose it as a classification problem. So if you have any object in a particular frame, and then your task could be that with some candidate windows or candidate windows. So if this is one window. So which one is basically you classify them as either background or the the object. So there could be, of course, in this way there could be more than one candidate, and again you can use some more post processing, but you expected that there will be only one such possible strong candidate. Now this is there, so you design a classifier. Again, the classifier is almost similar to like computation of correlation. So it's a linear classifier. As you know, when you consider, if I represent this object as a vector, so this classifier means, say it's a hyperplane W transpose X, and suppose if it is the object, I will make it 1, else say I will make it -1 or 0. So I have to design. So here in the discriminative tracker, you have some data, level data with you. So it's a classification problem. It's basically the same thing like you train a model to compute these coefficients in this model and then apply it for subsequent operations. And this operation can be also considered as a correlation operation that we will see. That's why in discriminative tracker we find essentially that many of these trackers are like a correlation filter. In fact, we call them correlation filters in many contexts. So let me just explain that part. So in this case, as I mentioned, the tracking is a kind of a detection problem which classifies a background from foreground. Foreground is that object. So if you have pairs of training image and its output, say FIGI, so you have to design a classifier, and output could be in the form of 0, 1 or -1, +1, or it could be a regression also. So sometimes in the training level data, we give a possible location, as you understand that when something is moving in the object space, so there are certain uncertainties. At some location you have a very high score, and around that location you have a decaying scores. So though they could be quite strong just around it. So the problem here would be to make exactly this score. So you have to compute the probabilities, regress the probabilities in this zone, and whichever is wherever you get the peak, you consider that is the position of the object. So this is a kind of regression problem. In that way, it becomes also a regression problem, or rather than the classification problem. But in our context, we may consider both of them, as we can consider here. So as I mentioned that it is something like correlation operations, because what you do that you perform when you are performing the correlation, say you have this pattern here, this is your template appearance model, it may be in the feature, and this is a candidate with zone where you have another appearance model. So you take the correlation between these two. What you do, you simply perform the dot products. So if I represent it as a vector, you simply perform the dot product. But let me formally define the correlation. So correlation can be considered as a correlation filter. So you perform this as a function over the space itself, over the domain itself. So you perform at every point this operation, and wherever the object is present, has been the evidence there, it would be very high. So the similar pattern you get there, it will be very high. So this is that particular computations. That is what is correlation. And in the image, you can also extend it to the two-dimensional case. You just see that it looks like convolution, but what happens that in convolution, the mask is inverted, temporally or spatially inverted, but in correlation it is in the same direction. So the relationship in the Fourier domain is also quite similar. So convolution, we know that it's a multiplication operations. Say if you have the filter, if you have the f, and if I perform the convolution operation with h, so we know that their Fourier transform, suppose this Fourier transform of f is, let me explain ff, and Fourier transform of h is fh. So you just multiply them. So what you get, Fourier transform of their output. So if y equal to f star h, so you get f of y in this case. But in correlation filter, what happens that this actually you take the complex conjugate of that, and then so if it is a correlation, then you take the complex one. That is a difference, because as I mentioned that the temporal inversions or those things are there, that is related, it can be shown very well. So this is this pointwise multiplication is shown by this operator, and f is the Fourier transform of f, that function f, and h is the Fourier transform of function y, function h, and g is the Fourier transform of its output. For images also, it is the same relationships for two-dimensional Fourier transforms. So I mentioned that this operation is, this symbol denotes the complex conjugate part. So your problem is that if I give you the level data of tracking, so object locations in consecutive frame or a set of frames, you have to learn H. So what is the optimal representation? So which means that basically you have to learn this is acting like a weight, and so, or it is giving something like an appearance model, what we have discussed earlier. So your optimization function should be, in this case, that you have to you have to compute that H which will minimize the square of this error for every observation I. So let us first revisit this method of linear regression, because correlation can be expressed as a linear operation, as I mentioned. So in this case, the problem statement is that if I consider the pairs of your corresponding the vector where actually the respective. So the vector in that in the frame where the object has been moved. So you are correlating with respect to them, and you know what is the result. So yi. So it is something once again like classifier that vector whether it is the same or not. It belongs to the same object for the frame itself. So the correlation computations or filtering operation is expressed in this way. You take the dot product of this coefficients w with this vector, or you can write it as in the matrix from w transpose xi equal to yi for all I. So in general, we are assuming any values of yi in your problem domain. So in this case, let me represent this data in the form of a data matrix. As you know that all vectors could be represented in the form of a column matrix. This is the usual practice to denote the data as a data matrix. So it becomes a two-dimensional matrix. As you can see, the columns are the vectors here. And similarly, the respective observations, they are also represented by a column vector. For convenience, I have used a row vector form. That's why this transpose is considered. So if this equation can be expressed in the form of a matrix multiplications as a set of equations, and then your objective is to so as I said that what you can do, that we are trying to get if I write that because you understand that these are column vectors, so I should write x transpose w equals y. So this is how you consider here. Now if these samples are row vector, then of course this transpose is not required. It depends how you are writing it. So let me see. Here I am writing w transpose x. So the w has been here. So it is okay. W is taken as a row vector, and then so you are minimizing it. But for ridge regression, we also regularize w. That means we try to minimize the magnitude of the w. So it's a linear combination of these two. So the problem is that you have to get w which will minimizing it. Now this can be solved algebraically by using least square error technique, and you can get, so if I consider this is error e, so if I take the partial derivatives with respect to individual components of W, and as a system of equations we can write it in this form. It has the advantage, this is, linear operations can be easily expressed in this way. So it gives a compact form of all these equations. So we can see that it is quite very intuitive, because it's a square operation. So a derivative means any derivative 2x, say this square, so 2 into this entity plus the derivative of this one, which will be x transpose. So that is what is, and from here also you get lambda, the same way lambda W transpose. So you are deriving with respect to W. So this set gives you an equation, set of equations. This is a set of equations, and from there you get this a solution. This is actually a least square error solutions. So for this, so you see that this is a kind of covariance matrix with respect to the data matrix, and this is another term. Now this computation, as you understand, it requires inversion. It is quite in a way intensive computation, costly. So to avoid inversion, what we do, so what we can express this computation in the Fourier domain, and we can perform this. We will see that how we can do that. In some cases they are convenient. So one of the early work on that kind of correlation filter is a kernelized correlation filter, kernelized. So first let me explain the case what we have discussed here. So in this case, it's once again it's a core component of the tracker is a discriminative classifier, and as you understand, this we have already mentioned, that distinguishes between target and background, and it is trained with scaled and translated image patches to cope with natural scene changes. So that is the important thing that we understand, that every target has a filter on its own. So no filter is an universal. So with respect to that training images, you are designing a filter. So and in this case, the trick is that just taking a single observation, you can generate many versions. It's a kind of data augmentation. So you can do as translation and rotation, like a vector. If I translate and rotate, I get several observations, and we can represent it as a circulant data matrix. And there are certain properties of circulant data matrix which can be exploited to compute that operations, as I was discussing, the estimation operations using regression efficiently. So let me first explain what is this circulant matrix. So here, as you can see that if in the circulant matrix is formed, say you consider every row is your data matrix, and then you are simply what you are doing, you are rotating it. You are rotating in this direction and shifting it. So this is the next row. Then this is the next row. So in this way you go, and this is what the circular matrix looks like. Pictorially also it can be shown in this fashion. This is a pictorial fashion. So the relationship for circular matrix in the Fourier transform space is interesting. So with respect to this, now this is x actually. This is x. So if I take the Fourier transform, let me explain a small x. If I take the Fourier transform and diagonalize this matrix, then the inverse Fourier transform will give me the circular matrix max. So this is inverse. So this is a DFT matrix, and this is the Hermitian transpose. So this is what Fourier transform of a vector x is this one, and this is a DFT matrix Hermitian. So the relationship has been, we have discussed earlier also this thing. You should note that this is a normalization factor. So DFT F is not an orthonormal matrix in that sense. So it will make it orthonormal. So if I use the ridge regression using the circulant matrix representation, then the solution could be simplified or could be expressed conveniently in the Fourier domain. So once again, let me give you the solution here. Now, if I assume these are complex entities, then this can be equivalently represented using Hermitian transpose. When everything is real, then this is represented in this form. because when you are doing the Fourier transform, you consider the general case. So now, as we have discussed that this covariance matrix in the complex domain, it could be expressed in this form, and finally, as you can see, which is actually the inverse of the diagonal matrix formed by the pointwise multiplication of these two, that Fourier transform of X using complex conjugate and this one. So you can understand that both of them, this will be a real number. This will be a real number actually, and you take the inverse Fourier transforms, you will get this one. So XHX plus lambda I can be expressed in this way, and XHY also can be expressed by following the similar logic. So everything is coming into the diagonal, and as you can see, all are diagonal matrices, and their inverse will give you the respective quantities, what you get it here. And this inversion operation, when you perform in the transform domain, we write it in this form. Actually, it is a pointwise division. You should note that this is a pointwise. So this is how the this coefficients of that linear combination or the filter weights are computed in the Fourier domain. So you have to take the inverse DFT to get the actual filter coefficients. So note the numerator. So it is pointwise multiplication of the complex conjugate of the target model, that means that vector, input vector, and also the Fourier transform of the respective output vector which has been given, and the denominator is expressed in this way. But these are all fraction denotes element wise division, but that you should note here. So once you get it, then you invert it, and then you get the filter, and then you apply it for finding the pattern. So this is the correlation filter. This is how you get it. But in a more general scenario, in that paper it has been discussed, and that is the interesting part of this theory, that even nonlinear models also can be accommodated. It's again that kernel trick. That's what we do. What we do, that you map the feature vector to a high dimensional space, and effectively, which means that there is a function which is mapping xi to a high dimensional space. Okay, so phi xi denotes that high dimensional space representation. But using kernel trick, we really do not require explicit representation, because what we have seen earlier, we are simply computing the dot products of different quantities. So even these high dimensional vectors, what is required essentially that dot products of those respective pairwise elements of that vectors. So and also the linear combination, that the weights, it can be considered as the linear combination of these high dimensional vectors, training vectors. Now this is that dual representation. Alpha is a dual representation. So if I use this same form of correlation filter, so we have W transpose phi z for any test, which means that I have to compute, once again, as I mentioned, that every computation is basically a kind of dot product of two vectors. So you have to model the dot products only, and that is what is kernel trick. So you have to define a kernel which will provide you those values directly. Now it could be defined in terms of some functional forms which assumes like a properties of this, which takes care of properties of this kernel, and so this is kernel functions. So as you know that earlier also we discussed, there could be kernel functions like Gaussian function, so, and which can provide you the kernel matrix where the elements, these elements are expressed in this way. So the optimization problem would be written in this form, the same optimization problem, and when I convert this thing using the kernel values, then actually now instead of minimizing over W, you have to minimize over alpha. This equation. So then these are the data elements. So the kernel function value is invariant to ordering of dimensions. That is important. The property should be, the functional value should be invariant to ordering of dimension. Suppose you are computing distances. Now, Euclidean distance, that is free from ordering of dimensions. Because no, if I reorder them, respective dimensions will be also coming to the repositioned. Respective values will be repositioned in the same dimension. So, overall distance value remains the same. Even for Gaussian function, it is true. Then actually what we can show that the kernel derived from the columns of circulant matrix is also circulant. So that circulant matrix property remains also true when we are deriving kernel from a circulant, because that is important. Then only you can apply the theory that we discussed. The assumption was that we handled circulant matrix. Then only the respective diagonalizations with using the Fourier transform of the base vector forming circular matrix that holds. So that's why this is what, if you take the first row of that respective circular matrix, kernel matrix with respect to these values, then if those circular matrix also will give you the kernel. So the solution for this nonlinear regression, as I have considered, so this is the weight vector, and this is the functions that you need to evaluate. So you actually would like to find alpha, and it is given in this form, which is once again, which is y. It is Fourier transform of y, and also Fourier transform of that y vector, column vector, and Fourier transform of the first row of the kernel matrix, and then lambda. So from there you get this solution. So this is what, and as I mentioned, there could be different kernels, there could be Gaussian kernel, or there could be linear kernel, and using them you can get this alpha. And once you know the alpha, then you take the inverse transform and you can get this fz. You can use it for tracking an object subsequently. So with this, just let me summarize whatever thing we discussed under this topic of object tracking. So that object tracking means you have to estimate an object trajectory in an image plane as it moves. That is the objective there. And we discussed about optical flow, which is a distribution of apparent velocities of movement of brightness pattern in an image, and the governing equation for determining the optical flow is given by this. That means grad of I in the space, and with the dot product with its apparent, that velocity profile for that point, that should be equal to the negative of the differential change over time, or overall the brightness value, the brightness pattern along the motion of the object, it remains same. So this is what we used. We have discussed also KLT tracker, where it is a similar concept has been exploited, but you provide the treatment in a bit different way, where you are trying to solve this problem. So you have to find out that displacement, D is here displacement, which will satisfy it, and from there you can estimate D. And then we discussed about recursive Bayesian tracking, where you have to compute the state of an object which is under movement at kth instance, given the observation from 1 to k, and recursively, if you know the corresponding state information at the k-1th instance with its past observations only till k-1. So it's kind of a dynamic programming, I should say, once again in the probabilistic framework, and we discussed about that. And one of the special case of that tracking framework is Kalman filtering, that we discussed. Then we considered graph-based method, where it is basically the kind of computation of longest path with accumulated evidence from source to destination in a directed acyclic graph. So that is what is the crux, and from there we try to get the trajectory. We can use also on-the-fly greedy approach instead of considering an offline or buffered approach, and that would make the operation more applicable in the real-time scenario. And So the multipath tracking is and technical methodology is employed there. And finally, for discriminative approaches, we consider kernelized correlation filter. We discussed about correlation filter, and from there, we have seen that how the concept of circular matrix can be used to formulate the problem or to adapt the problem in that scenario, varying scenario where the target appearance may change and provide robustness. Not only that, that data set that can be easily generated, like some kind of augmentation. But the basic point is that when you have a circular matrix as a data with its corresponding levels, then you can apply easily the Fourier transform operations on those base vectors because there is a property of diagonalization of the circular matrix in the Fourier domain. So that is very interesting, and we exploited that, and we have discussed the methods using this kind of kernels for designing those filters. With this, so let me stop here, and this is now end of this topic particularly. Thank you very much for your patience and listening.